arrivare. Ciao, ciao italiani. We are, cioè, proviamo sulla casa, eccetera, eccetera. E qui io poi dopo faccio introduzione a casa, in post edit. Puoi aggiungere i sottotitoli con le facce, eccetera, eccetera.
Per esempio, se lo facciamo qui prima di andare via, possiamo andare in bianco perché già qui c'è l'MP3, lo metto qui dentro e ho l'audio mix, quindi possiamo usare i microfoni, i radiomicrofoni che ci apprendiamo, cioè possiamo fare quello che vogliamo. E qui è molto comodo.
E per quello diciamo infatti che alla fine di tutto, se loro possono passare anche in video. Vediamo se potete creare, che ne so, avete qualcuno sul qua della parte grafica?
Della parte video,
okay.
Però sì,
una slide dall'inizio, quindi all'entrata, che ne so, anche solo EASM 2015, eccetera, che cambia prima di ognuno, no? Quindi poi riparti. La slide class consentito è 2015, presentazione, copiano le sue e poi cambia.
Facciamo un intervento con il video di istruzione caso.
Ma infatti, tipo, se ognuno di loro fa un pezzettino corto, e poi dopo puoi lasciare sotto il link alla parte completa. Sì, guardi, vi aiuta sempre molto con, poi dopo una volta fatta questa cosa la mandate alla stampa e se volete vi do il contatto.
Lo posso chiedere, non lo so, adesso solo se puoi scusare.
Perché i giornalisti sono molto pigri, perché se gli mandate tutta quanta la conferenza non lo guarderanno mai. Ma se gli mandate dei pezzi così, loro possono prendere nota e scrivere gli articoli veloci. Cioè, se è una cosa molto più in breve,
più o meno, no?
Non ci consultiamo su questo.
No, allora dico
tu sai cosa vuoi fare e io ti seguo.
讲厕所也都修。
something is missing out to the in any case, it's time for us to cover the experimental rocketry to be. As I said before, the young association is launching our rocket model. Stefan Grazio, is Vice President of Skyward Corpus Rocket. So, experimental rocket.
Hi, everyone. As you will say, I'm mission, and I'm going to not bore you at all. I'm going to describe you why our association is producing now was able to organize all this, and I will just give some historical detail about the association. So let's begin. So Skyward has been founded in 2012 by a group of 10 students. I'm very glad to say that I was part of that group of students, and we usually spend the night, talking about rocketry, von Braun, stuff like that. And we had dream, to design, to build, and launch a something rocket. But we didn't know how to do that. We didn't have even the financial resources to do that. So we searched for help. And this help came from the Politecnico. Now, from 10 that we are now 80 people. There is a strong collaboration between us and this university. The university gave us the space to work in university. Now, what are our targets as a student association? We want to deepen the knowledge of the students inside the technology used in a real project like this one, a Sound Rocket. And as a matter of fact, we want to have a project to the theoretical studies that is done in this university. It's about not doing studies, but it's theoretical. So we want to have a real project beside studies. More, other than that, we wanted to break the record for the European made rocket by students already. It's now set by Dutch guys of the University of Delft at 21 kilometers, just like a week ago, more or less. Other than that, to do that, we developed a program. It's called the EASM program. That is a 3-step rocket-based program. What I mean, in order to achieve higher altitudes, we couldn't think to, build at the first step with a rocket, because you didn't know even how to organize a group of 8 people to work. You didn't know even how to organize a group of people, such a group of people, even to have a meeting or just have dinner together. So, 1 kilometer first step, and for this step, the rocket was with someone else. And I'm going to talk about a bit about someone else. And he said, okay, everyone, why don't we test our organization? We're students, okay, but we have to know if we're able to work in this kind of project. It's not very easy, you know. So we built Persona Next. We launched it 3 times. Once in November 2013 and two times on June 2014. Persona Next is a rocket that you can see in the stand outside this classroom and is 2.2 meters tall, 9 centimeters wide, so it's a small rocket, but we built it and launched it. So this is very important. So this is the reason why we did it. That's how we work, as I said. And I wanted to show you, this flight on June 2014 because we recovered it 2 times successfully. So we proved that the rocket was reusable. I mean, the propellant was one, but okay, the dispatch was recovered safely. So we want to show you a bit about the day. Okay. Now, I would love to talk to you about all the details that were very useful during the launch and during the design parts, because that are the little details that are important in this kind of project. But in order to explain you better what are our next projects in the future, for the 2 years, next launch, I would like to invite you, very considered, it's my friend, and it is the project manager for the 7th Alpha. He's going to talk about this kind of
Okay, good afternoon. I'm Gabriele Consiglio, the manager of Vaxxan to Alpha, and I'm glad to show you some technical details about this new rocket that we are going to build. So, first of all, I would like to start from the name to Alpha, because actually as you saw before, our next rocket will be actually 2x. So why 2 alpha? This is a rocket that we are building in order to test those systems that actually will fly on Roxanne 2x. So in order to accomplish the mission, this rocket will be powered by a solid rocket motor with an average thrust of about 8,000 newtons and a total impulse of 50,000 newton seconds. So, what about the structure? First of all, the structural design, as you easily can think, it's a quite hard task to do because we have to satisfy all the needs coming from the other working teams. So it's always a compromise between those needs. And for which reasons, we decided to build this rocket almost by using the carbon fiber. And an important feature that we are going to implement with this rocket is the modularity. So we will use a model in order to have an easy way to extract and insert each system inside this picture. Of course, the second one is related to this second, and the last one will be occupied by the parachute and the there are some you will be and here there are some of the data. So the most will be long carbon profile made of sort of carbon fiber.
Ok.
Not going to that link is actually this one that is made of aluminum and has O-rings in order to allow the pressurization of the parachute vane in order to get the nostril injected and we want to deploy the rope. So fuselage, as we said before, is made of carbon fiber and these sections. So what about the recovery systems? Here, an important a fixed point of the Skyward Association is the fact to recover all the rockets. So we want to recover completely the rocket after each mission. In this picture, you can see the Roxanne 1X. So here there is the Gloger with the nostrum, and here there is the Roxanne 1X with its parachute. Okay, so the entry system, the recovery system of R1X is composed by, of course, drogue and main parachute, ejection system, and release system. Here you can see some details. So the drogue was actually a circular shape parachute that will can slow down the rocket up to a velocity of 20 meters per second. And the main parachute is a physical shaped parachute. So the ejection system was made by CO2 cartridge and an air tank that has the function of pressurize the parachute vane. And the release system is composed completely by mechanical stuff, as you can see. So, motor, hooks, so on. But okay, what we are going to test on Roxanne 2 Alpha? We want to test a new kind of system in order to have a guided wing, a guided parachute that is actually the Rogallo wing. The Rogallo wing is used even today for paragliding in case of emergency. So it's a it's a triangular parachute that can be guided by pulling the strings. So we can guide the missile back towards an enemy area. The detection system or Roxanne 2 Alpha will be more or less the same. We actually use two CO2 cartridges and a valve system that will pressurize the parachute plane in order to eject the moonstone and let the rocket be deployed. We are going to use two drones. The first one will be a circular shaped drone in order to begin to stabilize the rocket from the apogee. So the descent velocity will be about 40 seconds. And okay. The second drone parachute shape that is more stable and will slow down the velocity up to 20 meters per second. The release system actually will be quite different from the Roxanne 1X. So we will use a hot wire cutter in order to cut the shortcuts of the drones. And so it's not a mechanical system as the Roxanne 1X. Okay. Okay, what about the Rogallo wing? The Rogallo wing will be deployed at more or less 1,000 meters. And it's actuated by this device here. So you can see the two DC motors and the two pulleys that actually pull the strings of the parachute in order to guide the rocket as we want. Mission analysis. So let's move to mission analysis. And what we are developed up to now is a simulator. A simulator for what we regard the ascent phase. That is a 6 degrees of freedom simulator. So the rocket during the ascent phase is modeled as a rigid body. And for what regard the descent phase, we actually are using a 3 degrees of freedom simulator. So the rocket with the parachute is modeled as a material body. How does the simulation work? We take the aerodynamic coefficient and those parameters related to the aerodynamics from missile.com. That is a software developed by the American Defense. And so, of course, the mass properties and motor properties are taken from the structural department and the body department. So we put those parameters inside the simulator. That is a custom wing model, so let's say quite simple. And the non-release effect is taken into account. So as I said before, 6 degrees of freedom for the ascent phase and 3 degrees of freedom for the descending phase. But what we are going to do for the next rockets is this. So we actually want to do CFD analysis, so computational fluid dynamics analysis, and we want to do some wind tunnel test in order to get a more reliable data and a more precise simulation. So we want also to improve the model, so we will not no more a constant new model, but a model that is quite. We want to take into account the Coriolis effects, because the next rocket will reach a higher altitude, and so this is how to make it. And now, what about the control? The aim of the association is to develop a control system that actually is able to control the altitude and so reach your role of the rocket. For what regards the Roxanne 2 alpha, we are using a control system only on the roll axis. And we want also to develop at the same time a control system for the same place. So a system that is able to guide back the rocket. Okay, what does what are we going to do on Roxanne 2 alpha? So control the roll angle, as I said before, by means of canal pins. We have studied also other systems like the reaction wheels, the cold gas system, but we end up that this canal configuration has a better stability, performances, and trajectory. So we will implement this system inside the Roxanne 2 alpha. Of course, the improvements for the future are the control pitch and UL. Okay. So the aim is to make the rocket land slowly in a safe area by using the Rodalo ring. And why actually? Because it's a research field that is not so studied, let's say. So the improvements for the future are coming back to the trajectory to guide the rocket back to the launch site. In this picture, you can see the 3D model of the control system. So these are the 4 pins that are driven by these 4 servo motors. And this is the calibration platforms for the, of course, the calibration of the sensors. So, last but not least, the electronic systems. The electronics brain is actually the brain of the rocket. Okay? So, the electronics drive all those systems. What we have, let's see, what we did after is one board as the brain of the entire system, so the Roxanne 1X. So Roxanne 1X actually had only one board, an interfacing platform to connect the sensor to CPU and central processing unit. And the Roxanne 1X had only one transmission channel to transmit data to the ground station. What we are going to do on Roxanne 2 alpha, first of all, at the same time, business for those sensors are actually MEMS, so micro electromechanical systems, accelerometers, gyroscopes, magnetometers, and design choice in order to reduce manufacturing costs. So we want to build one main board and other daughter board that will be put inside each section of the rocket in order to drive the subsystem, the rocket. The feature of Roxanne Alpha is the fact that we will have actually three channels. So one, the first channel is at a low frequency and low data rate, and this channel is dedicated for the telemetry and security signals. The second channel will be used for the multimedia flow, and we will have also a third channel used as a backup. And this is the last feature that we are going to implement, so optical pattern recognition algorithm for control with descent. So what does it mean? It means that we will have on board the Roxanne Alpha a camera that is able to recognize the terrain patterns by using algorithm in order to spot the most suitable area to land. So with this very amazing feature, I finish my presentation of Roxanne Alpha. Here in the picture you can see that the area is suitable for landing. And that's it. I thank you for your attention. And now Christian Lazzaro will explain you some details about the hybrid rocket we are here.
So, good afternoon. First of all, thank you for being here. I'm glad to see so many people here to see what we do, what our colleagues do. And second of all, I'm Christian Liardero, and I'm the project manager for HRE 100T, which by the time it's done, will be the first time I have representing why we are building after successful launch of we decided to make a little step further in the technological development of the engine. So we decided to go hybrid, actually. And the main goal of this is smaller. The main mission mission totally pulse. So this is where the main comes from. So it's 100T, which is 100,000. For the development of it, we decided to choose like oxidizer, the nitrous oxide, and the like fuel, the paraffin. This is the choice due to the fact that this is probably the most common mixture you can find on the web. So we could actually find so many data online. We could compare our data with some other guys' data. Then actually, nitrous oxide and paraffin are very easy to find on the market, so we can buy it quite easily. And then nitrous oxide is a very nice gas because it's self-pressurized, so we don't need any pressure system. The design result gives an average thrust of 5 kilonewtons and total burn time of 20 seconds. So the preliminary size of the model is this. I'm just focusing on the fuel and the oxidizer. So right now we have a total mass of 80 kilos of nitrous oxide, which is a lot. We in a tank at the 70 bar, which is a lot. So So the tank in this case would have a volume of 0.14 meters. Actually, the number doesn't mean anything to me. But if I say that it's 4 meters long and has a diameter of 20 centimeters, maybe you will have the right idea. So the solid fuel is paraffin, actually is a mixture. 9% of paraffin additives. The green is a simple cylinder with a cylindrical hole for the pole. Then we have here other details, but actually it's the preliminary sizing, so I just read that. But this system, we have aluminum pipe. The important thing is that we have a self-actuated valve. And our motor brings like 2.5 kilograms per second of nitrous oxide. So not like a Ferrari, but something like that. So how do we do it? This is our project plan. We have a 2 to 3 years campaign of tests. So the first segment will list from 1 to 1.5 years. And in this segment, we will try to understand how our system is developed, how the various auxiliary systems are going together. So we will try to fix all the hardware needed to make the future firing test. In fact, in the test campaign number 2, we light the fire. That means we assemble the motor, we fire it. The test campaign 2 gives nice results, so we can continue with the last campaign, which is the shoulder, which is the qualification test campaign. So we have to make three tests in which the model will be fired like in nominal condition of flight. So if only one test fails, we have to go back to the test campaign number 1, and so the test campaign number 2, and so on. But the hardware are very tough. They have so many problems actually. This is the project review process. So we are engineering students, we have to use engineering models. For example, a system, we have some design requirements which are pretty unknown. So we have the PDR, which is an acronym for preliminary design review. It's a phase in which it demonstrates that the preliminary design is the system requirements within acceptable risk and within the cost and the schedule constraints. So after the preliminary design review, we have actually like some month of design reviews in which I meet the various team and we discuss about the development of the project. So it's not so short. After so many design reviews, we have the CDR, which is a critical design review. It's critical because it demonstrates that the maturity of the design is appropriate to proceed with the fabrication, assembly, integration, and test. So here we have a process along at least 5 months. Then we have the test. After the test, if the test fails, we go back to the PDR. If the test is okay, we have the integration of the systems and every problem model. So those are the upcoming objectives. In this first say period of time, we have to build a basic test facility, which means we have to build something like this. And it's useful because we have to understand how the nitrous oxide behaves inside our tanks. So we have to understand how to transfer nitrous oxide from the tanks we buy inside the main tank of the rocket. And then we are also to understand how it behaves inside the injection segment. So the injection actually determines the quality of the combustion. So if we fail the injection studies, the model cannot go very high. To do this, we need also a REDAS, which is an acronym for Rocket Engine Data Acquisition Systems and Control. Actually, it's like the nervous systems of the rocket. So we have like a central console, which is the brain, which is the remote control. Then we have the REDAS, which is a pretty huge and complex system which controls every valve, so monitor the thermocouples and so on. This is what I was talking about. So this is the basic class facility. We have, of course, the structure, which there is one tank. Actually, this is pretty small. It's not the full this long one. This is due to the fact that we want to test nitrous oxide inside a small tank before moving to the other one. So this is actually a dummy tank that we use to experiment with the nitrous oxide. We have the model test stand. So this is the model you see in the other room. And this is the HNRS. I say it is the condensation tank. Actually, the name is a heat and noise reduction system. So this is the project of this thing is due to the fact that the test area was we found the test area which was actually like the park of a fabric. So the owner told us that we could test the model there, but we needed something that reduced the heat and noise. So it's pretty strange, but we had to do this. But we have not built it yet. I hope to not build it. Then we have a breakdown and final cooling segment in which the hot gases here are deflected inside a water cooler. So this is a deflection grid, and we hope that the hot gases here just become condensated, and the water here evaporates. So we have just a big vapor grid. Then we have the water tank and pump, which is the water that we take to alimentate the system. Those are the subsequent objectives. We want to build an expanded test facility. What I mean is this. Actually, we want to proceed test activities in a field and professional environment. So we are engineers who want to be, and we want a professional environment. We have to take the test facility is in order to have the possibility to test and make research on the several rocket engines and multiple sizes. We want to apply the engineering notions and practical activities. And maybe the most important thing is we want to involve other staff, students, organizations, common activities, work on nationwide, Europe-wide projects. This is the test facility. Actually, this is the core of it. So we have a complete template structure, which we can attach different tanks of various sizes. And we have the model workbench area. So we need to call it a model test stand because we need it so we want to like a small work which this is actually story for rocket science. So the last thing I'm going to say is that very soon there will be a contest who wants to give the name to our mother. So just follow this link and you can give the name or the name you want to our mother. Thank you.
Thank you so much. Hi everyone. I'm Andrea Gatti and I'm the project manager of the Zero Program. Okay, we are. This project started almost 1 year ago when I had a question. I said, is it possible to launch our rocket from 8,000 meters? The answer was yes, we can. And why? Why we have to launch it from 8,000 meters and not from the ground? I would say only the second. We are in plan to build an aircraft for for each rocket. So we are building the first one for the first rocket, the EASM 1X. And the reason of launching from 8,000 meters is that if you launch a rocket where the areas are required, the same rocket could gain the apogee altitude from the 60 to the 80%, and talking of the same rocket. So you can save money. So the other target of our team, of course, is design and build this aircraft. We won't buy it. It's we need a particular aircraft. I will show you next why we need a particular aircraft. So we want to design, build, and of course test this new aircraft. And the other particular thing is that we can simply build an aircraft when we are launching a rocket. We can say to the people that gives us the euros, we can say, hey, we want to build an aircraft just for flying two times per year. It doesn't function. You must build an aircraft that is capable of doing also other things. Other things like does not like launching rockets. Why a new aircraft? It's the first question when you want to build a new aircraft. Is it available on the market? No, simply the reason. Because you can buy on the market, on the net, you can buy for a few thousand euros. Basically, it doesn't work because we want to fly very high and we want to fly for just 1 hour. It's a completely different project. All the drones in commerce, they have a serious lack of high altitude performance. And if you want to launch our rocket, we must do a particular maneuver that the drones in commerce simply can't. Also, we have a problem. The rocket installation. The rocket is a very long tube, not much more. And the drones in commerce have a propeller, mostly in the fuselage. So there is a simple problem of clearance from the propeller and the rocket. You must choose for a multi-engine aircraft, but it's very hard to find. And of course, they are piston engine. They have a serious lack of performance while they climb over 6,000 meters. The mission profile. We can buy an aircraft that is e-commerce because our mission is just to land, put the engine at the maximum continuous power after the takeoff, climb, launch the rocket, and then return to the base. In drone e-commerce, I said that they can fly also up to 20 hours. It's a completely different project if you are building an aircraft. And of course, for us, it's a great opportunity for how to build a new aircraft that will be our job. So this is the project. We have chosen a current configuration because it allows us to save some drag. So install smaller engines, less cost, less fuel. That's a good idea, I agree. But this will recover a system because if you want to fly this kind of aircraft in Italy, you must demonstrate that you can end the flight whenever you want. Whenever you want, meaning a structural failure, a double failure on the engines. And the number 2 of the engines is because if one engine fails during climb or during the launch, the other engine will be able to keep the aircraft flying until you reach the base and make it on the exit. And as I said before, we can we can load the rocket, but also other scientific instruments. And scientific instruments, while they are running, they need electricity. Yeah, we can provide it. Our payload pod will be fitted with an electrical line. And if your experiment needs to fly much than 1 hour, because 1 hour as a standard, our aircraft, as a standard endurance of about 1 hour, because we don't need more. On the payload pod, you can load also an auxiliary fuel tank, because there is a fuel line, and extend the endurance of the aircraft. If you are carrying, I don't know, scientific experience like some sensors that are really light, and you can fill the gap until 10 kilograms. That is our payload with fuel. Here there are some preliminary technical data. This maximum takeoff mass is 62 kilograms. It's data obtained by a statistical way of the drones that are actually flying the world. And then the other data are from our preliminary study. The possible user, I said before, you can carry and test while you are in high altitude conditions, the CANSAT and the CubeSat. Of course, the payload must be under 10 kilograms because we can't carry more. But of course, you can test it. And we can do also meteorological application. This one is a weather balloon. It's very common to see if you live near an airport. They usually fly this kind of balloon almost twice every day, just for meteorological application and for the pilots arriving and departing from that base. And of course, our aircraft, due to the high altitude performance, is suitable for high altitude and flying research. You can load a sensor for solar radiation, fly until over 8,000 meters, collect some data, and then come back. Here is the timeline. The D-phase design is the detailed project of the aircraft, only with computer-aided technologies. And we'll start in a few weeks. We hope with the help of our teachers. And the C-phase, over after 1 year, it's the building of the structure, installing the ballistic parachute, the fuel line. In that phase, we will build the aircraft. And then we will start the flight test campaign. Because this aircraft, when we will be finished, you have to test it without the rocket aboard. Then we will test if it flies well as you designed. Then we will start loading a mass of 10 kilograms, simulating the rocket. And at the end, we will start the flight with the rocket and launch it. So, thank you very much. I finished my presentation. And if you have any question, we are here. Thank you very much.
We showed a lot of things. They probably seems overwhelming, I think, but we are following the society. We think big, we want to think big. Because if we got in less than 2 years of Roxanne 1X, we need, and we are sure that we need more support from everyone, because we hope that professors, institutions, and I don't know, probably companies and sponsors would help us in realizing these. I have to repeat big dreams, but we think that with cooperation we can achieve that. So, if we have time for your questions. If some of you, okay, thanks. I've heard also the IPTLs if you want to come here, so if they need a more specific answer, we can do this. We can answer.
Okay, you mentioned that the rocket you're building, Politecnico and Alpha,
Yeah.
The mass is 60 kilograms. Yeah. Which rocket was 60 kilograms of mass? Yeah. Could you tell the mass of the propellant?
About the engine of the...
It's 32 kilograms. It's a commercial model. It's Cesaroni technology Pro 150.
So it's commercial.
Yeah.
Okay. The second question you mentioned about wind tunnel tests. Yeah. I have a question whether these tests are somewhere here in Politecnico, the wind tunnel, or if you have somewhere to tell where, and whether it's subsonic, transonic, and which scale of the model.
Okay. Then here in Politecnico we have 3 wind tunnels. 2 are more deep. One is surely deductible, small, it's very slow. Even the big one is used mainly for cars, buildings, and I don't know, cycles probably. So we would like to firstly start with what we have here in Politecnico, then we have to check. We also checked on CIRA, that's the Center for Aeronautical Research here in Italy. They had transonic and supersonic wind tunnels. We have contacts, and we will check if we can test that.
And the scale of the rocket in the wind tunnel? Do you know maybe? It's full scale how?
Here, probably, we're going to use a skeleton rocket, something like Proxen 1X in the dimension. Probably we inside the tunnel. We have to check. But for, I don't know at the moment the size of the supersonic wind tunnels in the Chia center, so we have to check that. We probably, our intention is to base the majority of the plan and design on numerical means. So beside that one that is freely available, the 1997 version is freely available on our book. If you search well, you can find it. And it works because, or at least for Roxanne 1X, you got 30 meters of difference from our simulation and the average. So we want to, exploit for the majority of the design phase the numerical programs, the numerical softwares. And then obviously we want to check after in Italy or if we can with our phones and our support all over Europe. So I think scale progress for supersonic obviously. Any other questions? Okay. Okay, in any case, we have people out there who want to ask in a more formal environment. So, okay, that's all for what we have to say. Now we can go on with the presentation, with the conference. We've seen an outlook of all European programs all over Europe, but we have here, but the subject, the experimental rocket subject, is not something that is only European offices. Today, we have a great honor, we are very happy about that, to have friends and colleagues from Japan that travel to Milan to show to all of you what is the situation in Japan about experimental rocketry. So, I'm here, Dr. Kagawada from Chiba Institute of Technology, that will talk about that. Welcome here.
Thank you very much, very kind introduction for me. So at first, I would like to say to scientists about invite us a Japanese team for Professor Ken Galpetti and Skyward member and everyone. Thank you very much. So, thank you. So, I hope some collaboration of the rocket project between European students to Japanese students in the future. So, I would like to introduction to our activity of Japanese students. So, today's speaker is Japanese two guys. Okay, let's play presentation.
Thank you. So, my name is Kyohei Yashima, a student of Tokyo Tech. So, now start the introduction of the team. Okay. So, at first, outline of UNISEC and UNISEC. UNISEC is in Japan, a university student engineering consortium, and it is the NPU, non-profitable organization, that's for a particular educational activity in the field of space engineering. And EASM is UNISEC student organization. So EASM is made up only students. And it started in 2003. Now, 53 teams and about 190 students joined. Okay. So, EASM purpose is particle space development by library and cooperation among students. For example, library is hold competition or fund hour, and cooperation is sharing data or technology of satellite or rocket or space balloon or something, and management event. After this stage, I or he explain out. And UASM have 7 working groups. There is 5 special working groups and 2 common ones. Okay. Working groups are rocket and Kansai satellite and satellite, nano satellite or more big satellite. And others, GNS or balloon working group, PR or exchange working group there. So now, I belong to this working group, and rocket working group have 3 main streams. First, safety control. So we make we set standard for safety launching rocket. So about rocket structure or ground support equipment or avionics or also. And next, set a guideline. This is for new entry team. And now in Japan, out of team is entered to rocket working group. So we need guideline and give the guideline new entry team and make education. And last, arrangement of launch point. In Japan, mainly 3 launch points. But recently, especially Noshiro is so overcrowded to launch. So we use another launch point. So we may arrange each team to go to each launch point. So lastly, future plan of UASM rocket working group is finish up the guideline. Just now we writing guideline. So finish up the guideline throughout April in 2015. And for the future, rewriting division every year, I think. Next, division of safety standard. There are already safety standards, but it's a little old. So this year or next year we revise it. And last, this is new front. Whole lecture. This is about simulation. In Japan, generally we use open rocket, but it is not good. So we lecture how to use open rocket effectively or make new simulation or like that. So and how to make FRP, 5-hour for profit. My team can make GFRP or CFRP structure, but new entry team can make FRP saving. So we teach them to make how to make FRP. Okay, so that's all you need. Next, this is my team. I am president of this team, Create. This team is a team made up with students mainly from Tokyo, my school. And it was founded in 2008, nearly 9 years ago. And almost 20 people are in the team, so small team. And we launched in Noshiro, mainly Noshiro and Oshima. This is Japan, and Blue Point is Tokyo. We launched in August Noshiro, and November and March in Oshima. And so next is feature of Create. First, FRP structure. Our rocket is made by only CFRP and CFRP. And we use only our original CFRP and CFRP. Next, this is avionics board. Our avionics board is called SAB sub, standard avionics board. And this is so small, just about area is 2 centimeters by 4 centimeters, and height is just 10 millimeters. So, yeah. And lastly, we use hybrid mode, use hypertech mode. It runs oxidizer and solid fuel. Solid fuel is ABS. And recently activities. This year, March, in Osaka. Right picture is our rocket. But as a result, rocket was damaged in middle life because of the inflow of air into the nose cone. Our rocket nose cone is deployed half nose, so inflow and damage. At this time, estimate maximum speed of this rocket is 146 meters per second. This is most fastest speed in Japan hybrid rocket. And next, this is August 20th, about 2 months ago. This launch is toward the sea, but it flies ballistically. It can deploy parachute. And reason is the same as one Osima launch, so it is so diverse. And last, future plan, or create. Next launch will be November 14th and 15th, near 1 month before, at Osaka. And 2 rockets will be launched by team. And second, we start self-made engine project. Now we preparing for engineering model computing test at Osaka launch in November. For the last my part, please, if you're interested in our activity or another questions, please send a message or visit our homepage. Thank you. Is my friend, Chihado Tsuemata will talk about his team.
Okay. Good afternoon. I'm Chihado Tsuemata. I'm one of the member of student hybrid team in Japan, and I'm a project manager of my rocket team in the university. I will talk about organic student rocket project. The main purpose of our project is to practice the technical education, learn the technique, and the management skill during the actual training. We launched the rocket 2 times in a year, summer and winter. In summer, we launched at Noshiro. Noshiro City holds Noshiro Space event every year. It is one of the most active aerospace functioning event in Japanese students. In winter, we launched Taiki Town in Hokkaido. The winter project is our team private project, so we challenge more difficult, and so we spend whole year for it. We have highest absolute record in Japanese students. This rocket is H34. I want to show you our H34 landing movie. The rocket which is about 20 seconds. It's onboard camera. This rocket has two separation systems for 20 seconds. So parachute is open. Main parachute is at proper altitude to 200 meters. Its main parachute open. It's dropped down on the sea. Basically, we are trying to develop original engines. It made by the box and we use nitro oxide. Our box of engine can make 1 kilonewtons and 8,000 newtons sec on total inverse. Also, rocket project in March 2016. That's all. Thank you for listening.
This was very awesome. I think that everybody here agrees. So, there are any questions? I have one. Probably you said, but I didn't get probably. What was the apogee for that rocket that you, the apogee altitude for that rocket that you showed up for the video? What was the maximum altitude? Can you? For the last rocket you showed up. Okay. Yeah. Okay. I didn't get it. Sorry. Sorry. My fault. Okay. No?
2, 3, 2 minutes. Okay. Okay, perfect. Thank you. Sorry. Okay. So I don't know. What? Okay. A question there. The microphone.
Okay. Do you have any image of the main shoot of the rocket in the video? I mean, I want to know what is its shape? It's a conical, for how large it is. It's conical portion of it. It's okay. But the diameter plus 1.5. Thank you.
Okay. Someone else? Okay. I was thinking if it's not in the program, make a little pause. What do you think about that? Or we want to continue?
Senti un attimo, giusto per vedere se va bene.
Sì.
can start. Over. We have the annual conference. Just 1 minute. Okay, so we went overseas for a bit. We saw what is the situation in Japan, watched the great activities that are carried on there. So now we come back to Europe, and we have, because we have seen a lot of things to say. We go precisely in Poland with the Western Rocketry Group, David, that will present their activity. So welcome here, David. Thank you.
So, good afternoon, everyone. I'm Dariusz Cieśliński from Warsaw Rocket Group, from Warsaw University of Technology. I'm the head of Rocketry Group, and I want to show the development of the program of sounding rockets in Warsaw University of Technology. So, So about us, firstly, we are the part of Students Space Association. We are not the group itself. We are a part of an association which takes pride in CubeSats, in rovers. We took part in competition in NASA competition for moon rovers or Mars rovers also. We also make stratospheric balloons, but we now focus on my group, it's Rocket Group, and we can see the people of the group. There's about 30 people from Warsaw University of Technology, from some faculties, not only mechanical, but also civil engineering, electronics. And I can show you now the family of our rockets. We began the work in 2008, and for about 3 years it was the very beginning when the people from this group were thinking whether there is a possibility to build a rocket, whether we are able to build a rocket with our possibilities in financial case and abilities, engineering abilities. It appears that it's possible. We had a budget of about euros, it's maybe 120 euros, and we built the first rocket, Amelia 1. It was one stage, simple rocket, which aim was to show that yes, we can build the rocket. So, the maximum designing was about 600 meters, and the maximum velocity was 150 meters. There were two launches, and both of them succeeded. Only in the second start there was a problem with parachute, but actually the first rocket, the first flight, and the first full success. It was amazing. And the next rocket is Amelia 2. It's a two-stage rocket, actually almost full composite rocket, with a ceiling of 3 kilometers and maximum velocity of about 300 meters per second. What is significant, all the rockets are solid with solid propellant. We do not consider another method of propelling rockets, for example, hybrid or liquid, because there's no time and no possibilities for students, because students actually spend 2, maximum 3 years in a project, and there's actually no time and no resources to conduct hybrid tests, for example, from the very beginning. There were about 4 starts of this rocket, which I can tell more in the following shots. After another part of the development is H1. It's H family for rockets. H1 is one stage supersonic rocket, which was shot 3 times. And during the last tests in this October, it was 3rd and 17th October, we shot 2 H1 rockets, and then I can show all of you the results from the flight. And I can tell by far the ceiling is 7 kilometers, it's up below 7 kilometers, and maximum speed is 850 meters per second, which is Mach 2.5. What's next? We've got 3 rockets. These 3 rockets, and what about the future? So, to say it quickly, now we're developing a CANSAT launcher. I will not describe what CANSAT is because I think most of us know about this. And the aim is to reach the ceiling over 3 kilometers, lift 8 CANSATs on board, and the first flight shall be in 2017. What's the most important in this project? There are CANSAT competitions in Europe, but every CANSAT competition is held with altitude about 1, maybe 2 kilometers, not even more, and it can lift only 6 CANSATs on board once. And we want to reach ceiling over 3 kilometers with 8 CANSATs. The another way of our development is A2 class, which is almost similar as Amelia 2, but the only thing different is bigger engine in the first stage. And another project was H2 rocket, which shall be supersonic 2-stage, which was taken from H1, and it had to aim 30 kilometers. But later I will tell you why we resigned from this way. How do we work? I think we work as each rocket group. It contains a plan, code, build, test, release, and so on, and it goes in a loop as to the final success. Our area of interest. We design a rocket. We try to manufacture, do all most things to do on our own in order to be not to wait for external factories. We do also tests and simulations. Our main aim is to verify our simulations, our software, because what we do actually it's often that available software is not reliable. So what we do as mechanical engineers, we have some skills and we can make our own software. So what we do, we build the software and then we test. We make the flight tests in order to validate our models. So it makes us also more independent from the another commercial softwares. Design. We design our rockets in CATIA program, and we also try to make our own equipment for logistics. For example, there you can see our launch pad for rockets up to 80 kilograms. So it shows stand for us for a few years at least, because our rockets are not heavier than 25 kilograms by far. And there is a view of cap model of Amelia 2 rocket. And what we can see here, there are two similar rocket engines in two stages. Then we have here a parachute, which is opened by a nitrocellulose and a piston. In the second stage, a similar recovery system is parallel to the axis of the rocket, and the main problem is that we have an electronic device all in the head. So we shall not lose the head of the rocket, but the problem is that the parachute goes, we need to shoot out the head to get the parachute out. So in H1 rocket, we decided to make the recovery system normal to the axis. What we have next? Manufacture. The most important case in our rockets is the most innovative thing is that we make our own solid models. And the most important also is that they are composite from fiber and epoxy resin. And we design and make our own stand for engine production. When we make the composite on a steel pipe, then we heat it in a self-homemade oven with temperature profile which is related with the proper resin. For our resin, we use for composite, it's about 180 Celsius degrees for about 24 or more hours. 24 hours. Yeah, it's 24 hours for 180 degrees, and it can stand with this temperature for a time, so we think it's a really successful construction. Next, we need to take the composite out of the this steel body we were producing the engine with our next homemade mechanism. We also have our own workshop, but we have really a few possibilities to make. We still have a few possibilities to make the model, the manufacturing, the elements of rocket on our own. And as you can see, we cannot do this by our own. We need to make it outside the university. And it always extends the time of integrating the rocket. Simulations, as I said, is the most significant case for us. We conduct the simulations also in commercial. For example, ANSYS software, there's the relation between center of mass and center of shear stresses for flutter. It was calculated for a profile of tail. Below we have exhaust from the nozzle, and I also conducted as my thesis a model of static stability, because open rocket is not enough for us. We tried to find some test cases all over the world from wind tunnels, and then I tried to compose an analytical model which enables to calculate the location of the center of pressure, which stands for the static stability. I also compare it with CFD analysis. And then it appears that the composed model of analytical calculations from some papers and reports is even closer to the experimental results than CFD. So, to verify the static stability of rockets, we eliminated computation fluid dynamics. It's unnecessary in subsonic, transonic, and supersonic cases. It appears that analytical calculations are good enough. In case of drag force, it's our new case to validate. So it's on. We plan to compare the values we got from books with validated values from wind tunnels, then compare it to CFD, and verify whether there is also no need to use CFD. But we need to check it, and I hope we'll do it by the end of 2015. Experimental investigation. All the simulations would be useless if we had no reference values. So what do we do? I was asking about wind tunnels before because we also conduct wind tunnel tests. And at Warsaw University of Technology we have a wind tunnel for low speeds where we validated the case of static stability, but only for subsonic cases. And what is more, in a smaller wind tunnel for higher velocities, for example 100 meters per second, we were validating the deployment of parachute. We had to check the impulse force of the deploying of the parachute. And it appears that it's very similar to the experimental results. From our experimental results are very similar, or actually are the same as the NASA experimental results, and they really are very well with theoretical calculations from the NASA or NACA report. So it appears that there is also no need to validate it via CFD or with wind tunnel, but we had to check it. Can we have water? Excuse me. The most important cases, experimental cases, are stand tests on a bench of our rocket engines. We dispose two fully checked rocket engines. Fully means on a bench and in flight. And now, in this bench, we can see the rocket engine for H1 rocket. And now I can show the movie from the test for Amelia 2 rocket. And this is the curve, this one for this test. Could we start? Okay, thank you. As we can see, it was short because it works only, not only compared to other engines, it works 2 seconds and makes a thrust of about 700 newtons. It's also full composite before. And for H1 rocket engine, I had no movie. Sorry for that because I couldn't open it. But as we can see, it works 2.5 seconds and leads the medium thrust force about 4.5 kilonewton, and the maximum is 6,000 newtons. Tests. The most important of tests are most important, and the most important test of tests are flight tests, where we can conduct it. There's a problem in Poland, of course, as everywhere, I think. But we managed to find a military area almost in the center of Poland, in Toruń. It's artillery. It's an area for artillery tests, and as you can see some shots from this area, it's really hard to get to the start point. so with some military vehicles also. There's another mate who's carrying a rocket engine this way, because it's easier than taking it by vehicle. From tests, first test from 2011 was with Amelia 1. As I said before, it reached 600 meters. The first flight, there's a shot from the first flight, and it's fully success because the parachute deployed, we recovered the rocket, and it restarted next time. Another test. These are shots from Amelia 2 tests in 2013 and 2014. I have not the latest photos because the test was 5 days ago, and the presentation I said maybe 2 weeks, maybe or something like this. So I can show you the tests from last 2 years, and we can see the moment of going out of the launch pad, and it happens that we recover the Amelia 2 fully. Sometimes we can't really recover it fully. So we had a problem with parachutes as usual. And what is the most significant in this project? It's two-stage rocket. And for 4 flights, every time the separate system worked properly. So this is our success. It worked from the very beginning. In this project, we had a few times problem with ignition of the second stage, but the last test showed that the second stage ignited, and the rocket flew higher than with only one stage. So it's the next success, but we had the same problem with parachutes. So what we need to do is doing parachute science a lot. I can show the movies. The first one is upper, this is the second. It's the launch of A2 rocket, and what I can tell about the performance on the launch pad, it was 25 Gs and about 20-25 meters per second on the end of the launch pad. We can go next movie. Good. And there's a video from the camera inside the Amelia 2. There can be visible a moment of separation. It spins counterward. When it changes the direction, parachute. This time it was successful, deployment of the parachute. And when you could notice the rotation one direction, when it changed the direction, is the moment of the separation of the stages. And it's going down and down. We can avoid this because it crashed the land later, but it crashed the land in this way that the same stage was launched this year because there was no damage. Yeah, we can stop this movie. The latest tests from the 3rd October, we planned to launch H1 rocket into 2 H1 rockets because we had. And because of the problem with GPS in the second rocket, the H1 rocket, we fired only one H1 rocket, which can be seen on the launch pad. And there is a movie, if you could, yeah, can we? I love this. I always tell, look, and it's maybe half a second and then it's done. Yeah, could you repeat? Yeah. That's how it looks 55 meters per second at the end of launch pad and 40 Gs. Yeah, and the maximum velocity, I can tell you something more about the rocket. There are some shots from the military area of the time of the preparing of the rocket because it takes the longest time to prepare electronic devices, isn't it? Yeah, it's that less to get the third rocket, for example, because we had a flight time about 4 hours hours. Then during 4 hours we can launch 2 rockets. That's our achievement record. And about H1 rocket, I can tell, oh yeah, that's how we made it. We have problems with parachute, but why? Because of safety, we cannot open parachute in the apogee because the military area is really, it's not as big as we expect. So reaching the altitude, the apogee, there is a risk if we open the parachute, which helps rocket to reach the ground with the velocity of 7 meters per second. It appears that with stronger winds, for example, which were last year, it could flow to the forum. We could find it or in the military area or in the center of the town, or in Vistula River. So it was risky. So we decided to design a rocket in this way that it can withstand the impulse of the deployment of the parachute close to the maximum speed of the fall. Maximum velocity of fall is about 170 meters per second. It's almost to the velocity of one of the planes, I think. And it's about 700 kilometers per hour, I think. And that's how our rocket looks when it reaches the land with 700 kilometers per hour. As you can see, but it's a really nice landscape at least. It appeared that the parachute system worked because we planned to open it at the altitude between 4 and 5 kilometers. The apogee of this rocket was 6.5 kilometers, and we estimated that we need to open between 4 and 5, and it opened, but by the velocity of 160 meters per second, so it could be fractured. The parachute could be destroyed, so it only decelerated the velocity of the rocket up to 70 meters per second and it crashed the land. So all we have to do is to make two-stage parachute recovery system. That's our work for the next year. Flights versus models. As I was still telling you that the most important is to validate the model, this is our validation. As you can see, we had 3 measurements on board for altitude. Telemiga is a commercial computer dedicated for rockets. We had our own RTTY electronic device, and we had GPS from Telemiga, I think, because the blue and the green are from the pressure measurement, and violet is from GPS. As you can see, someone mentioned before that it's really hard to get proper information about the altitude of rockets from GPS, and this is why. You can see how it really looks, because about some significant value of velocity or acceleration, it needs to be shut down because it's treated as a weapon, GPS, and that's how it looks in practice. As you can see, the difference between for supersonic. In subsonic case for Omega 2, we had the difference between Kansas, close to the apogee, explosive bolts